All right, let's dive right into a really fundamental question in physics. It's one of those questions that sounds almost philosophical at first, but it underpins pretty much everything, from steam engines to exploding stars. And the question is this: does the universe care about the journey or just the destination? We're about to uncover the secret language that answers this, and it's all about telling the difference between what a system is and how it got there.
So let's start with that big idea. Does the journey matter or only the destination? In our lives, we hear all the time that it's the journey that counts. But what's so fascinating is that in the world of thermodynamics, well, sometimes the destination is the only thing that matters at all.
To really get a handle on this, let's use an analogy. Think about climbing a mountain. Your change in altitude? Well, that's simple, right? It's just the height of the peak minus the height where you started. It doesn't matter one bit if you took that long, winding scenic trail or if you scrambled straight up a dangerous cliff. But the calories you burned? Now that depends entirely on the path you took. That crazy climb definitely burned way more than the leisurely walk.
And this exact idea, this perfect split between properties that describe the destination, like your altitude, and properties that describe the journey, like the calories you burned, this is the absolute core principle we need to get our heads around to understand the physical world. In physics, we have names for these: state functions and path functions. And believe me, they are fundamental to everything.
Okay, so how do we actually describe the destination of a physical system? Let's say a container that's full of gas. We need some kind of coordinates, right? Something to pinpoint its exact condition at any given moment.
Well, these are called state variables. The best way to think of them is like a system's personal GPS coordinates. They give you a complete, perfect snapshot in time. If you know their values, you know everything you possibly need to know about the system's physical condition right now. You found it on the map of all its possible states.
And the most common coordinates are probably things you've heard of before: pressure, volume, and temperature, along with, of course, how much stuff you have, its composition, which we call N. If you can tell me those four things, you have perfectly, absolutely defined the state of that gas.
Now we get to the really cool part. Remember our mountain climb? Let's dig into the properties that act just like our altitude change, the ones that only care about where you end up, not how you got there.
These are our state functions. They are the ultimate destination properties. Any change in a state function depends only on the starting state and the ending state. The whole messy history of how it got from point A to point B, all the twists, all the turns, it's completely irrelevant. Now, what's really amazing here are the kinds of properties that fall into this category. The big one for us today is internal energy. Think of it as the grand total energy of every single particle in a system, all their kinetic energy from bouncing around and all their potential energy from interacting. It's a hugely fundamental quantity, and it's a state function. And you're about to see why that is so important.
But what about the journey properties? What's the thermodynamic version of the calories you burned on that mountain climb? Well, these are the properties that do depend on the path you take. And this slide really lays out the great divide. On one side, you've got your state functions, like internal energy. That's our altitude change. On the other side, you've got path functions, which describe the journey itself. And the two most famous path functions are heat and work. See, they aren't properties of a state. They describe the process of getting between states. They are all about the journey.
I know this can sound a little abstract, so let's make it super concrete. Imagine we have some gas trapped in a cylinder with a piston. We want to take it from some initial state, let's call it A, to a final state, which we'll call C. Now, there are a ton of ways to get there. For example, we could take path 1. First, we let the gas expand while keeping the pressure constant, and then we heat it up while keeping the volume constant. Or we could take path 2. First, we heat the gas up at constant volume, and then we let it expand at constant pressure. Both paths start at A and end at C, same exact destination. So here's the absolute kicker. Because internal energy is a state function, its total change, what we call delta U, has to be identical for both paths. It only cares about the start and end points A and C. But the work done by the gas, that's a whole other story. On a pressure-volume graph, work is the area under the curve, and you can see it plain as day. The area under path 2 is way bigger than the area under path 1. The work done is totally path-dependent.
And this is where one of the most powerful laws in the entire universe steps in, the first law of thermodynamics. It's really just an energy accounting rule. All it says is that the change in a system's internal energy, our delta U, is equal to the heat you add to it, Q,
minus the work the system does on its surroundings, W.
And right here is where the beautiful, undeniable logic clicks into place. If that change in internal energy, delta U, is the same for both paths, because it's a state function, but the work done, W, is different for each path, which we just saw from the graph, then for that equation to hold true, the heat transferred, Q, must also be different for each path. This is the slam dunk proof that heat, just like work, is a path function. It's all about the journey.
This brings us right to one of the single biggest misconceptions in all of science. Seriously, this trips up students all the time. The question is, can a system actually contain heat?
And the answer is a huge, definitive no. A system cannot contain heat any more than a person can contain a walk in the park. A system has internal energy. Heat is just the name we give to the process of transferring that energy because of a temperature difference. Heat is energy in transit. It describes the journey, not the destination.
So, if these state variables, pressure, volume, temperature, are what define a system's state, are they all totally independent? Can we just pick any random values we want for them?
Well, no. Turns out they're all tied together by the fundamental laws of physics, which we call equations of state. You can think of this like a rule book for matter. It's a mathematical relationship that puts constraints on the variables. It means you don't get to choose all of them on their own. Once you've picked a couple, the others are basically locked in.
In the most famous rule in that book, you've probably seen it. It's the ideal gas law. For a set amount of gas, this simple equation, PV equals nRT, tells you that if you know the pressure and you know the volume, the temperature isn't up for discussion. It's already been decided for you by the rulebook.
So, why? Why did we go through all of this? Why is this whole distinction between state and process, between journey and destination, so unbelievably important in physics?
Here it is. This is the deep insight. State functions are like a physicist's secret weapon because they take the entire messy, complicated history of a process and compress it down into a single, elegant, knowable point. Nature keeps its energy books balanced perfectly, but it doesn't care about the individual transactions, the little bits of heat and work that got it there. The fundamental laws of our universe are written in the language of states. They only care about what is true right here, right now.
And that brings us all the way back to where we started, but now with a totally new perspective. If the physical laws that literally build our entire universe are all written for the destination, what does that tell us about the real meaning of the journey? It's something to think about.